Yeah, I can do that. Well, this is actually nice. I can actually just do this. It's actually better than the laser pointer. It's certainly better for TV purposes. Okay. I'll use this too. All right, so this is not a new idea to people in this room, that there is such a thing as a smallest interval of time, the Planck time. And it comes from quantum gravity, combination of fundamental constants. So, and obviously, as we all know, a very small number, 5 times 10 to the minus 44 seconds, or 1.6 times 10 to the minus 33 centimeters. Expressed in particle energy, that's 10 to the 16 TeV, or 10 to the 19 GeV, so way beyond the reach of any plausible experiment, as we've thought. And of course, where that comes from is from the intersection of the quantum world and the relativity world, gravity. It's the length scale where a particle comes within its own Schwarzschild radius, if you like. And so that's the point at which we know the independent concepts, as theories put together, independent concepts of classical space-time and quantum mechanics that have to break down. You can't go to a smaller time than that. So that's a very interesting place to be, if you can get there. Now, it's seemingly impossible because the current technologies, right, the best microscopes we have are either smashing particles together in places like the LHC or the Tevatron, and an inverse TeV, which corresponds to 10 to the minus 18 meters. It's a very small distance, but it's still 10 to the 16 times bigger than the Planck length. Gravitational wave interferometers, your business here, are actually better than CERN at measuring small distances. Position differences can be measured 10 times better to 10 TeV scales for macroscopic bodies in interferometers. The important thing actually for this talk, though, isn't that. It's that those measurements are coherent position differences over a kilometer baseline, a macroscopic distance, which is not the case here. So that's actually the technology that I'm interested in. So what I want to talk about is not a way of smashing particles together and tearing things, quantum wave functions of particles apart at the Planck scale, but it's a way of studying positions and maybe thereby measuring a signature of the Planck scale directly using interferometers. So it uses gravitational wave technology, but it's not gravitational waves. It's better described as measuring a wave function of a space-time, and which describes not like normal wave functions would be position wave functions of bodies within a space-time, assuming a classical background. And this is actually just assuming that the space-time itself is described by a wave function, quantum mechanical style. The character of the effect I'm talking about is a transverse position uncertainty, and I'll talk a lot more about that. And it basically is an uncertainty which corresponds directly to the information limits or the entropy bounds that grew out of black hole physics, black hole thermodynamics. The name of the effect is holographic noise, and there's a prediction that you can make from these ideas with no parameters in it, essentially corresponding to a Planck diffraction limit. You suppose that you have a Planck radiation wavelength lambda and a transverse wave function of position at 2 places separated by L. In this case is going to be kilometer scale. L is the geometric mean of the Planck length and the macroscopic length, which is of course much bigger than the Planck length and thereby possibly detectable. So that's what I'm going to talk about. Now it turns out that for this purpose right now, the best machine for doing this is GEO600. And I'm going to come back to this later in the talk. The interesting thing about it is that they might have already detected the effect, and they're certainly detecting an effect at this level. So this is actual data of the noise curve from GEO600. So the square root of the power spectral density of equivalent gravitational waves observed is the blue curve, and the green curve is the noise model. And if you add to that the holographic noise prediction, which is the square root of half the Planck time for this apparatus, you get that green curve. So it makes up the difference for a mystery noise that they haven't been able to explain. So that's really the main reason to take the idea seriously, aside from all the beautiful ideas that I'm going to talk about. It's certainly accessible with current technology and may have been detected. So what are the ideas that go into this? The first one is that space-time, as you describe gravitational waves with it, is a classical manifold. We have Einstein's equations describing the behavior of that. In reality, we would like to think that it's a quantum system. We don't have a theory for the degrees of freedom for it, but it's, anyways, built into this idea is the idea that it's actually a quantum system. The holographic part of it is to say that it's a quantum theory in 2+1 dimensions instead of 3+1 dimensions. And the third space dimension is identified as the same as the dimension of time. So built into this, it builds in the causal structure of space-time. And again, I'll talk more about that too. But there's a class of theories like that, and which were constructed to agree with the holographic entry bounds from black hole physics. And then within that framework, positions are described as transverse wave functions on light sheets. So two-dimensional planes moving at the speed of light. And the whole system has a maximum frequency, the Planck frequency, that gives you the spread of the transverse wave function over macroscopic distances. That gives you that spread in position much larger than the Planck length. So that you can think of this as a measurement of quantum fluctuations in geometry. It's not the same, though, as zero-point fluctuations in gravitons. It's very different from that. And it's also not the same as Heisenberg uncertainty, right? I'm assuming that's negligible, actually, the sorts of things you're always trying to get rid of in your apparatus. It's actually a new effect, okay? And I'm going to, really the point of the talk is to motivate an experimental program studying the effect. It's, the basic ideas are on the archive. 2 papers have appeared in PhysRevD in the last year. Okay, so I want to start off by surveying why we should think about holography, because it's a very strange idea, and holographic theories of everything in particular. Nice quote from Tuft. This is what we found out about nature's bookkeeping system. The data can be written onto a surface, and the pen with which the data are written has a finite size. So 2 important and surprising things about that. First of all is the fact that any 3-dimensional volume can be specified completely by data on the surface. And so that as a volume gets bigger, the amount of information that you can get in it, and this is anything whatsoever, space-time plus any kind of fields, only grows as the surface area, not as the volume. It's very unfamiliar, not the same as, say, thermodynamic entropy in a chemical system, that it grows the area, which is also different to field theory with a UV cutoff. It implies some kind of non-locality. And the other part, the finite size, is that you only get 1 bit per Planck area, and that's sufficient to specify everything about it. If you take a surface and you divide up the surface into boxes, 10 to the minus 65 square centimeter per box, put a 0 or a 1 in each box, that's the number of ways of putting those zeros and ones is the total number of ways of assembling physics in that box. So that's a really surprising hypothesis. It's a very strange idea. And so it's worth going back into the rationale for that. So I'm going to go kind of quickly through this because there's a heritage that goes back over 30 years. And so just I'm going to go through each of these in turn. And they all kind of lead to the idea, consistent with the idea, that the theory that describes everything is a quantum theory on 2-dimensional, as they appear at our world, null surfaces with a Planck frequency bound. So the origin of that goes back to black hole thermodynamics in the early 70s. The idea that it was noticed then, right, that the behavior of black hole solutions of Einstein's equations exactly map onto laws of thermodynamics, in particular the second law, entropy always increases. There's a law of black holes, which is that the area of event horizons always increases and never decreases, just like entropy. And so then the idea came up that maybe you should just take that literally. Maybe a quarter of the event horizon area should be identified with the entropy, the degrees of freedom of a black hole, corresponding to the number of ways to make a black hole. Any way whatsoever, whatever you think of it. In other words, it actually has encoded in it all of physics that could go into the black hole. And that maybe that reflects something about the quantum gravity of the system. The deep reason for that is statistical, that there's the microscopic degrees of freedom guarantee that somehow. So that was already back in the 70s, and building on that was the idea that black holes evaporate, All right, so if black holes evaporate, it's not just black holes. This reinforces the idea that you can take the gravitational degrees of freedom, apparently a vacuum solution of Einstein's equations, and convert it into real particles and radiation at infinity, where you can really count the particles. And we know how to calculate the entropy of those things. Makes it look like that's really right. It really is an entropy. There was a long debate, and Kipps talked about this a lot, about is information really lost on the singularity, things like that. I mean, I think where that ended up was the idea that information isn't lost. It's encoded in gravitational degrees of freedom while the black hole is there, and as particles evaporate, the degrees of freedom are exchanged between the black hole, the localized ones of the black hole, and the propagating degrees of freedom of particles. So again, this revisits the idea that a black hole is completely described by information on a two-dimensional surface, the event horizon. It evaporates. Every time it evaporates a particle, it loses about 1 Planck area of the event horizon and shrinks. The total amount of information in the system is conserved, which is consistent with quantum mechanics. So again, I mean, this is very nice. We have the idea maybe is that quantum mechanics underlies everything. Now, so I've talked about black holes, but it's not just black holes. I mean, all of those ideas generalize to nearly flat space-time. You have unruh radiation. Any accelerating observer, you have an event horizon there. It's not a curved space-time, but you still get Hawking radiation. You still have an event horizon, and you still have effectively entropy bounds. And you can actually derive Jacobs and Trade. You can actually derive Einstein's equations from that argument. So it's a general property, perhaps, of the theory out of which classical general relativity grows, that it has this holographic character to it. So at 't Hooft and Susskind introduced the idea that, and this is where that quote came from this set of ideas, that there's something called a holographic principle, and it's that the whole world is holographic. It grows out of the idea that you want black holes to be quantum systems, and so everything has to be like that. It's encoded in 2+1 dimensions at the Planck scale. Those ideas can be made covariant and more rigorous in some ways discussed by Busso more recently. So the essential idea is that you can sort of guarantee that the right results come out for black hole entropy if you build the theory on light sheets, and that's the kind of the native formulation of whatever the theory is. Now, there's also been, in the kind of the theory of everything community, the unification community, exact examples of this kind of theory. I mean, it hasn't been done for the familiar world, the 3+1, but it's been done for extremal space-times. And so Andy de Sitter conformal theory correspondence is the famous example where you have a theory, a conformal field theory on a boundary, an n-dimensional system, which is exactly the same as or dual to a system in a higher number of dimensions with gravity. And so in those special cases, that's been shown to work as a duality, exact correspondence. So then again, it reinforces maybe the idea that maybe that's true for the real world, 3+1, the nearly Minkowski space we live in. Similarly, in string theory, there have been calculations for extremal black holes in higher dimensions, which let you count the degrees of freedom in the quantum system and come up with that number, showing that the argument is right. You actually do have microscopic degrees of freedom that agree with that same count, the entropy count from the Hawking-Bekenstein argument. They also give a strong indication that there's a minimum length. You go to a minimum length and you cross over into a dual theory, and you never get to a smaller length in the Planck scale. It begs the question of what the degrees of freedom look like in a realistic system, and that's one thing that I'm going to talk about in a little while. In fact, I'll do some of it right now. Taking one of these theories, matrix theory, and trying to tease out of that what an emergent space-time would look like. So this is about a 10-year-old theory now, Banks et al. And it's a theory which it's a quantum theory, and it's a candidate theory of everything. It's as according to the authors, it doesn't presume that there's a space-time, but space-time grows out of the theory. The fundamental objects are 9 n by n matrices, and then the 9 become 9 spatial dimensions. Okay, on a macroscopic scale, eventually, the n corresponds to the number of d0 branes, or basically particles in the system. And they show that there's a dual relationship with string theory. It's basically the same theory, probably. But anyway, there's a limit or an interpretation in which that set of matrices gives rise to 10 spatial dimensions, one of which is compact. So you think about a dimension which is the Planck scale, d0 branes which are Kaluza-Klein modes wrapped up on that scale, and then 9 larger spatial dimensions, and the whole system evolving with time as a quantum system. That doesn't look at all like our real worlds, and so how would our world come out of that? Well, first of all, oops, I didn't do that. Oh, thank you.
You running on battery by any chance?
Shouldn't be. No, it's okay. It was just it was Time Machine interrupting me. It's my fault. So, as usual in these things, you don't see all the 9 dimensions, and usually they say, oh, you see the three. But in this case, I'm saying no, only 2 of the 9 actually survive to be big, and the third spatial dimension is virtual. It's swept out by a 2-dimensional null sheet. So this is why the theory is holographic by construction. They write down this Lagrangian. You have a 2-dimensional sheet, and it's incompressible at the Planck scale in area on the 2-dimensional sheet. And so in a space-time diagram like this, each point corresponds to a 2-dimensional plane. The evolution of a sheet would be a vertical evolution of just the evolution of a 2-dimensional sheet. We live in a 3-dimensional world, and that's because we interpret this normal dimension to the sheet in our 3-dimensional world as a third spatial dimension, but it's the same as and is not independent from time. Okay, so null trajectories really are special. Null wavefronts really are special. They're the native way in which the quantum theory is formulated. So this is why I should mention that this is Einstein's thought experiment. As Einstein thought about what would it be like to write on a photon, well, these guys have an answer for that. If you write on a photon, it's a 2-dimensional sheet of these d0 branes in a Planck thickness membrane. That's what it is. If you go fast enough, that's what you see, or something like that. Anyway, that's not what I wanted to talk about. What I want to talk about is the macroscopic limit of this, the classical limit of all of that stuff. So they have a Hamiltonian, and this is their Hamiltonian. There's one scale, which is the Planck scale, which is the width of that sheet. Okay, and then you have these 9 matrices, which are the I's. There are 9 I's and J's. There's a generalized commutation relation. These are all the other standard model fields. And the trace here is taken over the n, so over the number of particles. So you take the trace, and that gives you macroscopic bodies. It's averaging over all that stuff. So the interesting thing is that all that, we think, Mark and I think, goes away when you think about macroscopic scales. The behavior is dominated by the first term, which is the kinetic term. So these commutation relations mean that it doesn't look like a space-time at all. It's non-commutative geometry. It's weird on the Planck scale. But on large scales, that's not important, and it's dominated by this term. And you can just see how that equation maps onto this one, right? The Hamiltonian is a time derivative, right? This is the square of a conjugate momentum to a position, and that disappears. So the matrix theory Hamiltonian becomes a Schrödinger equation, just a wave equation, okay, in one dimension, describing one spatial dimension plus time. So that's quantum mechanics. It doesn't have Planck's constant in it, but it does have the Planck length in it. And if you look at the solutions to that equation, they look like what I started talking about, which is a relationship between a macroscopic distance and a transverse one. This x dimension is the transverse dimension. And so this is what the modes look like in that wave solution. So this would be a candidate for the modes, not the same as field theory modes, but the sort of true dependent modes of the system. All right, so what are the observational consequences of that? That's sort of the That's the theoretical background. What if that's true? If space-time is a holographic quantum system like that, the world's formed by these Planck null waves, what does it look like from inside? If you're living inside it, what's the effect? Well, so one thing is that it does is it implements that entropy bound, the covariant entropy bound. It gives you the right number of degrees of freedom. And in particular, that gives you a sort of a bandwidth limit of space-time states. There's less information in the system, in any system, than you thought if you assumed quantization at the Planck scale. So like any hologram, the world's blurry. Okay, there's a limited information content, and it's sort of like if you imagine yourself in flatline, you suppress another dimension. This is like imagining ourselves living in a hologram. If it's a very good hologram because it's made out of Planck scale waves, it's almost perfect illusion, but there's a slight blurriness to the system. So this is a way of understanding the quantitative blurriness. Where does the number come from? And it's just from diffraction, just from the wave array correspondence of optics. So imagine that you have an aperture d, and you have wavelength lambda radiation, which is going to be the Planck wavelength in our case, so that there's an angular resolution diffraction limit of lambda over d for that aperture. So there's a diffraction spot for the aperture at any given distance, which has a physical size L times lambda over d. So if you want to ask, well, if you go to the ray description of the system, and all you know is that the endpoints of one endpoint is in the aperture and the other point is in the image, the diffraction spot, the minimum uncertainty in the orientation of the ray occurs when the aperture is the same size as its diffraction spot. So you just equate those numbers, right? So you equate d with L lambda over d, and you find that d is the geometric mean of the wavelength and the separation. And this is the basic same effect as what I'm talking about for holographic noise, except that in the metaphor that's developed, the size of the aperture or the size of the diffraction spot correspond to the transverse position wave functions of things. If you like, the electromagnetic field of this wave corresponds to a wave function of space-time position, and so this is expresses the relationship of positions at two different times, two different normal separations to one of these two-dimensional sheets. Now what? I didn't do that either. That's not even on this screen. All right. Somebody. So can I go back to what I was doing? Maybe. Okay. Okay. All right. So just think about a real hologram. In a laboratory, you have optical light, sort of micron scale light. You're looking at a distance of about a meter. The blurriness, the geometric mean of those two is about a millimeter. That's the typical blurring of a hologram. If you try to make the pupil of your eye out of the inside a hologram and look at things, that's how blurry things would be. You could make a larger aperture, you get better paths, but then the arrival positions are correspondingly blurry. So so that's the basic level of the effect. But then you just change that to the Planck length, and that's what the world might be like. So you in that discussion, the space-time positions are wave functions, and just like in the case of a diffraction system like that, the wave functions on these two wavefronts are Fourier transforms of each other, and so their standard deviations have that relationship. So it isn't that mysterious. The math is pretty simple. It's just the same as the familiar examples from optics. I mean, you do see diffraction patterns on a scale much bigger than a wavelength all the time. I have to go over that. You can also talk about, what time is it? 3:30. I'll get through here kind of quickly. You you're talking about the diffraction limit of a Planck wavelength telescope, right? The Heisenberg uncertainty principle, we talk about measuring the position of a body with radiation, and there's a conjugate relationship between the uncertainty in the measured position of the thing and the momentum of the radiation you use to measure it, right? And we're used to this idea. You have an uncertainty relationship, and so those observables don't have an independent classical meaning. Well, it's just, the same is true here. That is, the positions, these two positions don't have independent classical meaning. The construction is a little bit different. We're making an image of a body with Planck wavelength radiation, and where it has that diffraction limit that I just discussed. So, you can map these things. They're not exactly the same, but the idea of holographic uncertainty is it is a quantum mechanical uncertainty, and it has it's limited by it doesn't have Planck's constant in it, but it has Planck's length in it. And the state of the metric that you end up with depends on the measurement just the same as the state of a body depends on the measurement that you do in Heisenberg uncertainty. So the approach to the classical limit is an interesting one. It's kind of unfamiliar. If you go to the Planck length, right? I mean, the system looks two-dimensional, and it looks, the way to see that is that you can write down the angular uncertainty, which is the square root of L Planck over L. So as you go to, if L is really small, you go to systems which are almost a Planck scale apart. The third dimension basically goes away. The angular uncertainty goes up to radians. So it becomes two-dimensional and three-dimensional. And as you go to, conversely, as you go to larger macroscopic systems, it becomes more and more precisely three-dimensional. Angles become less uncertain. On the other hand, in absolute length terms, it actually becomes fuzzier at larger separations, just like this diffraction pattern does, right? If you go to larger separation, the angle of the diffraction pattern gets smaller, but the size of the diffraction pattern gets bigger, and it grows like the square root of the size of the system. So that is not the usual classical limit of field theory, and you actually get this indeterminacy on macroscopic scales much bigger than we used to see. Sorry, I didn't want to skip that. So one example of this, again, if you make a world like this, it's a consistent quantum system. That is, when a black hole evaporates and the degrees of freedom go off to infinity, if you didn't have this kind of angular uncertainty in the positions of the products, then it would require, the farther the photons, the products, the evaporata go, the more information it takes to specify their angular position, because they're going farther and farther away. If you have the angular uncertainty, the holographic uncertainty in angle, and they go far away and they're fuzzy, then it has the same amount of information at all times. Okay, so it actually makes a consistent story. So that a black hole embedded in a distant holographically uncertain space-time is one that can be made unitary. So now I want to talk about interferometers, because this is really where you can actually talk about how would you see the blurriness, how would you actually measure and detect it. So as I said, the interferometers have this property of measuring. They measure non-local position relationships. They're coherent over kilometer scale, and they have a very high precision, 10 to the minus 20 or less. They go halfway to the Planck scale, and they measure transverse position. They have all the things you need to measure the effect. The fact that you have very heavy proof masses, you go to the standard quantum limit, you get the Heisenberg uncertainty low, means that you can talk about a system which is maybe limited by the holographic uncertainty. And so in a system like this one, you might actually have a coherent way to measure those positional relationships.
You go back for a second.
Yeah.
So psi started out being some wave function on n by 9 dimensional matrix.
Yeah. Yeah. Yeah.
And then, so that's a wave function on a very, very, very large space.
Yeah.
And then you said, okay, some spatial dimensions don't matter.
Yeah.
Most of them. But then there should have been sort of larger n should a little bit large, right? For the number of particles involved, or are you thinking of one particle?
I'm thinking of one particle. I mean, basically, you take a trace over. I mean, it's just the position of a macroscopic body. That's what reducing it down to one position and one dimension.
Okay.
You know,
So that
I mean, in reality.
So the Schrödinger-like equation you wrote down
Yeah.
was for the position of one particle.
Yeah, like the whole surface of an optic and an interferometer. That's right. Yeah, that's the idea. Obviously, a slight oversimplification, right? So in that language, right? In an interferometer, you have a beam splitter. You have sorry, I always do this in different directions. Wavefronts come and they interact twice with the beam splitter. There's a wavefront goes once down one arm, the other part of it goes through the beam splitter, and then comes back and interacts a second time. And you measure the signal here, and the phase you measure depends on the difference in the integrated distance along those two arms. That's what you do in gravitational wave systems. So here what I'm saying is that you at these two reflection events, they're separated by a certain amount of time. The first one happens, and later on the second one happens. That corresponds to a longitudinal, a normal separation in this wavefront frame. And so there's a certain, the beam splitter moves, basically. There's a random drift, approximately a Planck length per Planck time, between the first and the second of those reflections. And that means that there's a measured effect in the signal. Okay, so you map on the language I introduced a little earlier. The position wave function of the beam splitter has got these standard deviations at those two times. And so there's an apparent arm length difference, which is a random variable. You get the variance from that, and that's a measurable effect. And it doesn't have any parameters in it. It has the length of the arm and the Planck length, and that's it. So there ought to be noise at that level in any system like this. So you can make that, you can do it more carefully by using wave optics. And I'll just sketch how that goes. I mean, there's a paper that goes, it's basically lifted out of Bohr and Wolf, okay? I mean, you take the theory of complex amplitudes in diffraction. You have an aperture and you have a screen, and the aperture corresponds to the first reflection and the screen corresponds to the second reflection. And the intensity of the light corresponds to a probability, and the complex amplitude of the field in the optical system, corresponds to the complex wave function in quantum mechanics, specifying the position of the optic. So so you just put that in, and you can get the factors of 2 out. You set the wavelength equal to the Planck wavelength because that matches the holographic degrees of freedom from black holes and so on. So that isn't a parameter either. But it's basically the same ideas that I talked about, just with the factors of 2 included. If you wanted to go back to the M-theory interpretation, right? We had these normal modes of the system. If you have an interferometer with a certain limited size, right? The way to think about this, instead of a random walk, is in terms of spreading of a wave packet. You have a reflection, say, which fixes the position of the beam splitter at one time, and if you measured it at one time, it would then spread until the second measurement, and the spread between those two times gives you the indeterminacy, okay, or the measured noise in the signal. The fact that the system is a limited size, the length of the arms, it imposes a high-pass filter. You don't detect modes that you don't get any spreading below a certain frequency, given by the length of the arms. So, roughly speaking, it acts like a bounded random walk. At high frequencies, it looks like the beam splitter is randomly walking, but actually, because it doesn't include very low frequencies, it doesn't random walk forever. It random walks out to what corresponds to the width corresponding to the length of the arms. So the wave packet spreads a certain amount, and after that, it's just samplings of the position correspond to independently sampled random variables from that interval. So as a result of that, you get holographic noise. You get whatever you do, you can't get rid of something that acts like a set of shear perturbations. As I tried to show, this really it emerges. It's not really specific to matrix theory. It's a general property of holographic quantum geometry. It's also, the other thing about it is that it's only it has a shear character. It's not the same as a strain. It's transverse to a null wavefront. It's not the same as a strain. So the way to estimate the power spectral density, this is just a rough number. So this was the angle that I gave, right? That's just from the same number that I was given before. And so you would say that that dispersion at the characteristic variance at the characteristic frequency of the system has to have a power spectral density such that when you multiply it by a frequency, you get that. Or if you dimensionless number, h squared, just the Planck time. Okay. Now, this is kind of an aside, this one slide. That's all for computing at the frequency corresponding to a round trip time along an arm. At longer times, lower frequencies, it still looks flat. And the reason for that is that, okay, so here's the definition of the effective power spectral density. That's the apparent arm length difference, okay? The variance in arm length difference. Well, if you have an averaging time which is 1 over f, lower frequency, longer times, it reduces the variance. You're getting just like, like multiple measurements are going to reduce, like 1 over root t, the precision of the measurement. But that still gives you, with these formulas, that still gives you constant apparent power spectral density. With that same number. It's just the one number. The power spectral density is just given by the Planck time, or the Planck time over 2 in some systems. So some peculiar properties of holographic noise, because it really isn't the same as a lot of noise that you might be used to. So first of all, it's not, you can't get this by quantizing gravity. I mean, there is no physical perturbation mode of GR that looks like this. It's a shear mode. So in flat space, there's no classical space-time degrees of freedom that correspond to that. It's not a gravitational wave. It's not a strain. It's more like a sampling or pixelation noise. It's a limited amount of information in the system, which leads to that noise in the final product. So a way to look at it is that it's a bandwidth-limited precision. If you have a certain limiting frequency, Planck frequency, it's a limit on the amount of information that the space-time can carry about positions, remote positions. And you actually need that in order for the number of distinguishable positions not to exceed the holographic bound. If that's the number of different states of the interferometer, if you're not going to exceed holographic bounds, you have to have that kind of noise in it. So there's no curvature in the system. And the other part of that, the shear character, is that you can't detect it if you only do a purely radial measurement of position. But you could detect a gravitational wave that way if you had very good clocks. You can measure the stretching of space-time. This does not show up in that kind of measurement. So in GEO, right, you have, the reason it's such a good system for detecting holographic noise is that it sends the whole recycled power through the beam splitter, 2.7 or 3 kilowatts or something like that. It's relatively simple to calculate the amount of noise that you expect. This is the square root of half the Planck time, or in their bigger noise budget. It comes in looking like that. Okay, so it's right in there as a significant source of noise in the system. So I sent that number after I calculated. I sent it to Stefan Hilt, and he sent me back this plot where this is what I showed at the beginning. The blue is their measured noise. The green was their noise model at that time in June. And then he just added the number that I sent him, the holographic noise prediction, to the green curve, and he got that green curve, which agrees just exactly right. It's, as far as Karsten says, it agrees to within a few percent. There's obviously some other lower frequency noise that is still not explained, and it's some other lower frequency noise. So I don't explain all of the mystery noise, but it does explain, apparently it exactly explains, with no parameters, all the mystery noise above about 500 hertz, as far as they can measure it, up into this region. So what about LIGO? This is just from one of the LIGO papers, the measured noise. You could put the naive estimate for holographic noise on that, and it's above the LIGO noise, which makes it look like it's not consistent with the LIGO measurement. But that, of course, that's naive. That's assuming that this strain plot is the same as the shear. And for LIGO, that's a seriously wrong thing to do, because the LIGO sensitivity, as you all know, is highly enhanced by the fact that you have Fabry-Perot cavities that amplify, increase the sensitivity, the signal response to gravitational waves, but they don't increase the holographic noise, right? So in those units, right, I mean, this is so the effect is that if you have a normal incidence reflection, you're not sensitive to transverse positions. So the Fabry-Perot cavities don't detect holographic noise. So this is still a rough estimate, but I think you should take the naive one and divide it by about the square root of 150 or something, the number of reflections. It's 500?
Finesse, but it's not the way you say.
Whatever it is. I mean, yeah, thank you. But anyway, the square root of some number corresponding to the reflections in the cavities. And so it's actually below the detected noise, but not by a huge number, not by a huge amount.
Well, not if you, I might as well say it.
Yeah.
I have other things to tell you.
Yeah.
If you take the data, and I think Stefan came to you about that.
Yeah, he was going to cross-correlate, yeah.
At Texas, he
Yeah.
told me about it.
Yeah.
If you take the data that was taken between what we call H1 and H2,
Yeah.
and you reduce the H estimate after integrating,
Yeah.
because
Yeah.
I think your theory, at least unless it's when we talked about it,
Yeah.
you still had that two interferometers that share the same space within a distance that's much smaller.
Yeah, they should have it
and
in
the
common.
lengths are correlated.
That's
That's a
right.
very important part
That's right.
of your whole hypothesis.
That's right.
And what happens there is when you correlate those two detectors, which is done to look for an isotropic background,
Yeah.
you integrate, you go down, or you can make the number very quickly.
Yeah.
The H values are around 10 to the minus, let's call them 6 times 10 to the minus 23 at 100 hertz.
Okay.
At minimum. And then you say, that's for one interferometer, let's call it the 2 kilometer, because that's the one that dominates.
Yeah.
Then you say, okay, let's put the factor of 100 in, because of the fact that it is the beam splitter, not the ends. And so you're up at 10, let's call it 10 minus 22, you're up at 10 minus 20. And you integrate it for something of the order of 10 to the 7 seconds. It goes like a quarter power of that integration.
Right.
So you wind up with something not too far from it. It doesn't quite make it. Doesn't quite make it. It makes it around 4 or something.
With the current data.
With the current data.
Yeah.
I don't think we're going to
Yeah.
get any new data from the because
Okay.
we're not improving
Okay.
H.
So you can't
And
quite.
we're not doing H2 again
Yeah.
with the improvements. Okay.
Okay.
But that's so you know. It
That's
actually
exactly the right way.
Would have done it.
That's right.
The thing is,
Yeah.
that, so you know, yes, that's a reachable number. But
Yeah.
as long as look, do you mind if I? Or do you have more? You have lots more.
I have a little bit more. Why don't I
Please,
finish and then we'll
do
just
that, let's come
we'll
back.
pick it up. I just have a few more slides actually. So because actually some of these ideas are in there.
Yeah.
Anyway, so that is the bottom line. You know, if the effect is there, you can build a machine to see it, and the GEO600 technology is already there. They're already at that limit. In fact, so this is a summary of the current situation. They see noise that's compatible with it. They're not claiming that they're seeing it. It requires testing and confirmation. This is what Harold says. It's way too early to claim we might have seen something. But GEO600 is operating at that limit. The LIGO's not currently sensitive enough, and you can follow it up. You can do high frequency sampling. There's stuff you can do. If you wanted to prove the effect, you have to have a new apparatus or do something different, like coherent correlations. In the long run, where do you want it to go? Well, suppose they've already measured the noise. I mean, what they're doing is they are measuring directly the Planck time. They're not measuring it by measuring Newton's G and the Planck constant. They're doing it by measuring the Planck time. They're measuring it. So it's actually an independent way to get at that number. And of course, that opens up a new kind of physics you can do. You can compare that measurement with that measurement and try to see how precisely you get it. There's a lot, and then of course, to testing the character noise, the spectrum, the spatial correlation, the shear character, all of that. And I just wanted to mention, just one slide, the possible connection with dark energy stuff, because there is this class of holographic theories is moving in the right direction for that. You ask what the holographic blurring is, the delta x, at the Hubble length, the geometric mean of the Planck length and the Hubble length, that's 1/10 of a millimeter. All right, well, as we all know, the 1/10 of a millimeter to the -4 power, that is the dark energy density. Okay, that's kind of numerology. And there is a kind of there's a literature on that. There's something called holographic dark energy. There's not any real physics about it, but it means that the non-locality length for the dark energy, wherever the field theory modes structure is breaking down, that is the holographic displacement uncertainty at the Hubble length. So I don't claim to have an explanation here, but it does mean that you're studying the right kind of physics. You're studying this in the lab. It's the right place to be picking at it. Okay. Anyway, so this is what Ray was saying. If you wanted to go beyond gravitational wave detectors, so you can already go up to 1,000 hertz just with the systems as they are, but with similar techniques, you can go up to 100 kilohertz or even more. Going to higher frequencies is really great because you have a lot of things become easier. The suspension, isolation becomes easier. If you do this correlation, well, I guess it doesn't quite work but it almost does. But a new setup with the same idea would work. I mean, if you wanted to set up just a rough conceptual design for a dedicated experiment, you'd set up two interferometers near each other, macroscopic scale, 10 to 1,000 meters, I don't know. And they have to be much closer. You want them to be much closer than the total baseline, but not too close because you want them to be isolated from acoustic interferences. You want to have a high power cavity at the beam splitter, so you're not excluding holographic noise from the signal. And you want to sample it to high F, to whatever the free spectral range is of the apparatus, and then correlate the common holographic noise. And by doing the last step there, as Ray said, you can really quickly dig out the common signal from the two, which makes it, so especially since G0600 is already kind of a raw sensitivity there, this is obviously possible. So last slide. So what is there to do now on this thing? Well, first of all, there's a lot of homework to do. You have to calculate the transfer functions for the apparatus better. I think I've demonstrated there is a precise calculation to do, and I've done some, but not enough of them. And then, and also for other kinds of detectors, a better model that makes definite predictions. The high frequency correlation at LIGO is an important step to take. The upgrades at G0600 are happening anyway. They should be done with this in mind, and in particular going up to the free spectral range for the so way higher frequency than you would do for gravitational waves. There's also the idea that eventually you might want to do something very different, like an atom interferometer at small scales, very high frequencies, whenever that technology becomes competitive with this one. If it's competitive for gravitational waves, it's competitive for holographic noise, because this is actually corresponds at high frequencies to very intense gravitational waves. And the last thing is to do the matrix theory type connections better and engage to kind of figure out exactly what the scope, what types of theories are affected by this and impacted by the limits that you get. And I'll stop there.
Yeah, thanks.
Thanks.